Hello everyone, my name is Askar, and today I'm going to talk about complex analysis, basic complex algebra and conformal mapping. I'm going to start with basic complex algebra and move to conformal mapping, which is the main topic for our section. So the purpose of this lecture is to show that some real math can be really interesting, really mathematical, really beautiful, and really applicable. And there'll be a bonus section at the end. So let's start with a quick review on the complex numbers. As you know, z is written, or complex numbers, z can be written this way, where x and y are real numbers, and x is called a real part, and noted like this, and y is called an imaginary part, and noted like this. And if you don't remember, I is just one of the square roots of -1. So let's see how does actually our polar looks like in the space. So if we have, this is going to be, x-axis is going to be a real axis, and y-axis is going to be imaginary axis. So it means that here it's not going to be just 1, 2, 3, it's going to be I, 2i, 3i, and in the real part it's going to be 1, 2, usual numbers. So for example, number z, 3 plus 2i going to look like 2i here and 3 here. So here our z. So you have 2i on imaginary axis and 3 on the real axis. Also, it's very important to know how does the equation look like in polar coordinates. So it looks like z equals r cosine phi plus I sine phi. And as usual, r is the distance to origin from z, from the point, and phi is an angle between real axis and the vector. There's one really important theorem that used a lot in complex analysis for polar coordinates, and that if we have two numbers, z1 and z2, and we multiply them, then their lengths are going to multiply, and the argument is going to sum up. Very important formula we used a lot in complex analysis. Now let's take a look at conjugated module. Conjugate of z is just not like this, and it's just like that imaginary part have a different sign. So we just multiply by -1 the imaginary part, and we get a conjugate. So the module of complex number defined a little different than we used to define a module. So define like z square equals z times z conjugate. Now let's show really quick that z times z conjugate is actually a real function, not a complex. So it is x plus iy times x minus iy, which is x squared, x times iy minus x, iy times x cancel each other out, so we have negative I squared y squared, and I squared is -1, so we have x squared plus y squared. So this is a real function, which means that we can note like module z have to be greater than 0. So the actual value for module z is square root of x squared plus y squared. And it's real function and positive. So let's move on to the differentiation of a complex function. As you can see, the definition is almost the same, and this thing looks 100% the same. The only thing is the limits. The limit for a complex function exists if the limit of real part exists and the limit of imaginary part exists. There are 4 main types of function that we define in complex analysis. They are real to real, complex to real, real to complex, and complex to complex. So what does it mean when I say that? I mean, if you have function f of z equals to zw, then real to real means that the argument z is real and the result w is real. So complex to real is going to be z is complex and w is real. So real to real is that what we do in Calc 1 and Calc 2. Real to complex to real have very nice derivative. It's actually say here that it's either 0 or does not exist. So very nice derivative for complex to real. And for real to complex, there is this, you can simplify to this formula. There is no real simplification for complex to complex. As we do in real to real, there is just some nice ones, some don't nice ones, some you can have derivative. So we just need to do case by case. Okay, let's move to the main section of today, and it's conformal mapping. Conformal mapping is a transformation that preserves local angles between curves and rotation of the curves. So, for example, f of z. So what is transformation? It means that if we have f of z on some domain z and transform domain z into range w. So this is a transformation. For example, this is z and this is w. See, it looks like a square, now it's something different. So this is actually conformal mapping. What it does, it's, as you can see, all the angles here are 90 degrees. And it's still 90 degrees. You can see they all still 90 degrees. So it preserves an angle. So, and you're gonna ask me, why do we want to do that? This picture looks very ugly. In fact, we can do it back, for example, and now the picture looks much better. So we do a conformal mapping on ugly pictures that we don't like. We do conformal mapping. Now we have very nice pictures that we like to work with. We know how this works. And we prove some things for the new picture, and then trace back the results from new picture to the old ugly picture. So we can prove something for ugly picture without actually proving anything for ugly picture, which is really cool. So let's say, what does it mean to function to be conformal? So it has to be holomorphic and analytic. And what does it mean? It means that indifferentiable on the domain from both sides, and the derivative must be non-zero everywhere. So let's talk a little bit about why do I start doing this? Why do I start doing this project? So in my Calc 3 class, I saw this equation. It looked really simple, but very interesting, because it turns out that they called Cauchy-Riemann differential equations, and it's actually conditioned for analytic function or conformal function. So it's, in order function to be conformal, it has to satisfy these conditions. And let's actually check it for f of z equals z squared. So f of z, let's say, equals to u of xy plus I of v xy. This is actually what written here, what does it mean by I and v. So u is just real part and v is the imaginary part. So for z squared, we're going to have x plus iy squared, which is, for real part, is x squared minus y squared. Because if you open the brackets, I squared will be -1, and plus I times 2xy. So this is our u, and this is our v. Let's check du dv, partial derivative of u dx, and it's going to be 2x, right? And partial derivative for dv dy is also 2x, right? This one for y and this one for x. And so they're equal. First condition satisfied. And second condition, du dy equals to what? Equals to -2y. And dv dx equals to 2y. And then they have -1 difference, as we can see here. So z squared satisfies this condition. Now let's look at the picture f of z equals z. So it means that z squared is an analytic function. So let's paint our vertical lines in the red and horizontal lines in the blue. Then we're going to have that each angle between blue and red is 90 degrees. And so our usual our usual plane looks like, right? So if we make a conformal mapping f of z equals z squared, which we just proved that is conformal, then as you can see, the angles are preserved. So these angles are still 90. All degrees are still 90. And obviously blue lines are horizontal that used to be horizontal, and red lines that would used to be vertical. And there are some more examples, like f of z equals e to the z, also preserves all angles in conformal mapping. And like some weird function like this one, and it looks like some ear or something, and z cube looks very beautiful. So as you can see already, this figures looks very, very different, and for different types of conformal functions, we have very, very nice and different pictures, and we can front and back, and they're actually beautiful and very interesting. So let's move to the application. It's actually can be really, besides it's very interesting, and it can be really applicable. So it control mapping is used in cartography, physics, and engineering. There are a lot of problems for physics, engineering, and fluid mechanics, electrostatics, and heat conduction. So for example, here, this is scheme of electrostatic field, and the fixed solid lines like conductors, thin solid lines like potential lines, and dashed lines are electric fields. So the angles are actually 90 degrees everywhere. So when we do conformal mapping, we can do conformal mapping from A to B, and we're going to have very, very nice pictures that you can work with. And they actually do that and work with that one. So as I mentioned, that we do that, and people in physics do that because after you do conformal mapping, the picture looks way better and you can work with it. Also used in brain surgeries. So for example, the brain, there is an analytic function, conformal function that transforms it onto sphere, and all length is preserved, so you can do operations and surgeries looking at that picture, or the computer can help you looking at that picture, and which is really cool. And also it's used in 3D art. So if you do something in 3D, they actually use a conformal mapping for 3D models. So it's pretty cool how something that really just math can be beautiful, interesting, and very applicable. And now I'm going to show you a really extra bonus section that it can be really, really beautiful. So now it's going to be a Julia set. So Julia set is just a recursive formula that looks like this. And for each number C, there is such thing. There is such a nice picture. So we pick number C, and then we check for Z0. If the limit of, and we pick a Z0. If the limit for this Z0 and for this new recursive formula don't go to infinity, then we say that Z0 belongs to the Julia set. If it's, and we draw it, for example, here black. If it doesn't belong, we do it white. And the same here. And actually, if you start zooming in, it's not going to end. It's not like that, just like that's it. That's how a picture looks like. If you zoom in, it's going to look the same. Not the same, but in different patterns. But still, if you're zooming in, you can zoom in infinitely long time and still going to be zoom, zoom, zoom. Actually, I'm going to show it. So here, they're not like doing something. They're just zooming in. It's already done picture. They zoom in, zoom in, zoom in into parts, and it's changing. So thank you everybody for watching. I hope you like it. Bye bye.